This is Leo. Let's do some Leetcode today. So this Reconstruct itinerary, it's pretty hard, but once you understand how it's constructed, it's not that hard. So now we're given a list of airline tickets where tickets I equals to from I to I represents the departure and arrival airports of one flight. And let's reconstruct the itinerary in order to return it. So all of the tickets belong to a man who departs from JFK. So JFK is our starting point. The itinerary must begin with JFK, and if there are multiple valid itineraries, you should return the itinerary that has the smallest lexical order. So that's one more thing to think about. I'll read as a single string. So for example, the itinerary JFK LGA will be smaller in lexical order than JFK LGB. So we can assume that all tickets from at least one valid itinerary. We must use all the tickets once and only once. So how are we going to do that? This is basically a graph traversal, and every time we start with JFK. So suppose it has many neighbors, and we have to sort them before we go. We need to sort them into the lexical order. So we can go with the one with the least lexical order, then go backtracking. No, we never go backtracking. So we just traverse through it. Okay. So once we have reached all the edges, and we're done. Okay, so let's see how to work. So the first thing is to construct the map. It's not the map, it's the graph. Okay, so what are we going to do with the graph? We can use a hash map to do it. So everything is a string that is a key, and since we are going to we're going to sort all the neighbors in a lexical order, we are going to use a priority queue to maintain the order of each neighbor. So there we go, and I can call it a flights equals to new hash map. All right. So now we can make everything, we can build the graph. Okay, so for list of string ticket in tickets I equals to from to, so let's see, string from equals to ticket dot get 0 is the first element in the list, and string 2 equals to ticket dot get 1. All right, so now we're going to put them into the hash map. So flights dot compute if absent. We're going to use from as the key, and we're going to use a new priority queue as the value. All right, and in this case we're going to add 2 to our value. Okay, so now I think the graph is there. We can iterate the graph with JFK. So first let's set up a result, and we can return the result afterwards. So here we're going to traverse step 2, traverse the graph. Here we can use DFS or BFS. I'm going to use DFS for simplicity. Sorry. Okay, so DFS, I'm gonna go DFS. So what do we need here? We need a starting point, which is JFK. We need the flights. We also need the result to collect everything. Okay. So before we return, we must make sure that they are arranged in lexical order. Okay. So potentially make sure order is correct before return. Okay. So that, okay, cool. So now let's write the DFS function. I'm gonna call it a void function, and it starts with a string. Let's call it airport, and there's a map flights. Also, there will be a list of string as our result. Okay. So first, we need to get the priority queue. So priority queue string, and I'm gonna call it whatever, like arrivals. Okay. So it should be the flights.get airport. Okay. So now we have the priority queue as all the neighbors here. So we are going to traverse all the neighbors in a lexical order. Okay. So when do we traverse it? When there are when the arrivals is not null, and maybe it's not empty when there are still neighbors. All right. Okay. Then we can do the DFS. So we need the first element to start with. In this case, we're going to use the priority queue, which is arrivals dot pop, maybe poll. Okay. And the flights, the result. Okay. So the DFS goes to the neighbor, to the neighbor, to the neighbor, to the neighbor until it couldn't have any neighbors. So in this case, we're going to add this to our final result, and then go backwards. When there's no outgoing edges, we collect this and this and this. But remember, we're collecting them in a reversed order, reversed lexical order. So before returning the final result, we need to rearrange this. Okay, we need to reverse it. So the last step is to collect everything. That is result add what? At the last airport. Okay. Okay, cool. Sounds good. So here, yes, there's really a step 3. That is collections dot reverse the result. Okay. Let's try this one. Yeah, that sounds pretty fair. So let's do the complexity analysis. So constructing the graph takes O of E of edges, and the result will take at most spacing. Oh, let's go with the time complexity first. So we're going to traverse the graph DFS, and it should take like O of E, because we're going to iterate through every node in the graph. So the step 3, make sure the order is correct. In this case, we're going to use the time E log E because we're doing the collections dot reverse. Oh no, it's just reverse, so it is an E operation. Okay, I got it. So where does that coming from? Here we have a priority queue. Okay, so in this DFS we are going to pop everything from the priority queue, which takes log of E time. And how many times are we doing that? E. So the total time complexity is E log E. Therefore, this has a total complexity of O log E log E. Okay. And as for the space complexity, I think here we have a map which takes everything in there. So it should be like the length of the ticket. Okay. And we have a result to collect everything. Ideally, it could contain all the nodes plus one JFK. Okay, so it also is E. And the reverse, there's no extra space taken, so the total time space complexity will be O of E. Okay, yeah, that's it. Accept it. So thank you so much for watching. I'll see you next time.